We doing today? Hopefully y'all are doing well. For today's notes, which are going to be over VSEPR shapes, you're going to need your notes, you're going to need something to write with, and then you will also need a periodic table. So make sure you've got those, and let's go ahead and get started. So before we talk about what a VSEPR actually is, let's recognize that atoms and molecules specifically, form 3D shapes, right? So they're going to be forming shapes that are not just going to be on a flat line, they're instead going to be occupying a space that's kind of a three-dimensional shape, right? And when we're looking at these with our molecules, a lot of times it's fairly easy to represent them using a traditional geometric shape, like a pyramid or a cube or stuff like that, okay? So for this, we use what's called a VSEPR model. Okay, VSEPR stands for valence shell electron pair repulsion. So that's what we see right there. So valence shell electron pair repulsion. And basically what it's talking about is we are focused on the valence shell. We're talking about how those electron pairs will repulse. All right. So we're looking at this and we're trying to see, okay, well, if I've got valence electrons and they're kind of moving around, when electrons get close to each other, electrons have a negative charge. So if I get two electrons next to each other, they can actually, or two pairs of electrons next to each other, they'll start to repulse one another, right? They'll start to push away. And so the VSEPR model is kind of showing that repulsion that we see. Now, we do need to know how to do our Lewis structures for the valence, for the VSEPRs. And so that is something that you do need to, if you need to, go back and refer to the previous lesson over Lewis structures. All right. Okay, so with a VSEPR model, what we're looking at is, again, we're looking at that repulsion of those electrons. And repulsion stops where we are trying to minimize the repulsion that we have between our atoms inside of a molecular bond, right? So we're looking at those and we're trying to see, okay, well, what's the best way that these can be arranged so that there is the least amount of repulsion? And that's all about going back to the trying to achieve the most stable molecule that we can, right? Trying to reduce the amount of energy required to hold that bond together, all right? And so that's what we see when we're drawing these VSEPR models, all right? Now, there are some steps that you have to do for drawing a VSEPR shape. First off, you do need to draw your Lewis structure. Second, we're going to count the effective electron pairs on the central atom. Double and triple bonds are only going to count as one single bond, okay? And then we are going to arrange those electron pairs as far away as possible. Why? Because again, we're trying to minimize that repulsion. Okay, so let's take a look at HBr here. So first off, when you're drawing your Lewis structure, the first thing that you need to do is actually find out how many valence electrons they've got. So I've got hydrogen. Hydrogen has one valence electron. I've got bromine, and bromine has 7. So my total amount of electrons is 8. So when I'm done, I need to have 8 valence electrons. Okay, now I pick my central atom. Well, there's only 2 atoms here, so we're just going to pick one because they're basically just going to be side by side, right? And we spread them out as much as possible. Well, looking at this, can I really spread them out as far as possible, any further? No, I can't, right? If I bring this down a little bit further, it's going to be closer on this side. If I move it up, it's going to be closer on that side. So we can't do that at all, right? So that's going to stay as you see it right here. Now, then we need to spread out the rest of our electrons. I say fill the outer octet. So right here, I know that I need to have 8 valence electrons. This bond represents 2 valence electrons. So then I need to put the extra electrons around stuff that can hold it. Well, remember that hydrogen can only hold 2. It's one of those exceptions to the octet rule. So then all those extra electrons are going to have to go around bromine. So 1, 2, 3, 4, 5, 6. Okay, and so right there we see that our bromine has 2 electrons there, 2 electrons there, 2 electrons there, and 2 electrons there. So that bromine has 8. Hydrogen has the 2 from that bond there in the middle. And then the last thing is to double check and count all of our electrons up, 2, 4, 6, and 8. So we would have a total amount of 8 valence electrons. All right, so then this would be our Lewis structure for this. Now, looking at this, in general, this looks like basically just a flat line, right? We've got 2 points, and even if it's a 3D shape, just like my 2 fists here, if it's a 3D shape, it's basically a line between those 2 fists, right? So the molecular geometry that we would give this would be linear, okay, because it just represents a straight line, okay? Electron domain geometry is basically looking and seeing how many things are attached to that central atom, okay? So looking at this, how many things are attached to the central atom? Well, there's no central atom, so we would call this linear, okay? All right, let's take a look at the next one. So here I've got sulfur dioxide. So sulfur dioxide is SO2. Count up my valence electrons. I have 6 for sulfur. I have 12 for oxygen. So 6 plus 12 is 18. So then I need to pick a central atom. So what's going to be my central atom here? Well, sulfur. I typically look at these and I say, okay, well, which of these do I have fewer of? Because it's going to end up being my central atom. So sulfur paired up with oxygen here. And then I fill the outer octets. Okay, so I'm trying to fill the octets, or remember the 8 valence electrons, on the atoms that are on the outside of this molecule. So sulfur's not on the outside, so we're going to worry about it later. Oxygen is, so I need to fill it up. So right now I've got 2, then I got 4, 6, 8, and then I do the same thing with the other oxygen. So I've got 2 right here, 4, 6, 8. All right, so now I've got my valence electrons there around those outer octets. I'm going to erase these arrows. So now let's take a look at our central atom. So central atom currently has 2 right here and 2 right there. So we've got a total of 4 valence electrons attached to that sulfur. But remember, sulfur needs to have 8. It is not one of the exceptions, so it does need to have 8. Another thing to note is your central atom could have more than 8, but if it needs to have at least 8 if it's not one of those exceptions. Okay, so I need to have 8. Now, let's think about this. Where am I going to get those extra ones that I'm missing from? So I need to have 4 more, right? Because sulfur currently only has 4 attached, and it needs to have 4 more. So I need to have a total of 8. I've currently only got 4, so I need 4 more to add to it. All right, where do they come from? Well, let's count up our valence electrons. Again, I've got 2, 4, 6, and 8, and then 2, 4, 6, 8. So I've got a total of 16 electrons there, right? Well, I'm supposed to have a total of 18. Remember, that came from counting up our valence electrons, so I need to have 18 valence electrons. So I have 2 more that I can add. Well, remember, sulfur needs 2 more. So I'm going to go ahead and add those 2 valence electrons there. All right? Okay, now I've got those 2 added to that sulfur. Can I add 2 more? Well, no, I can't, right? Because I can only have 18 valence electrons, and currently I have 18 valence electrons. So then how do I satisfy this octet for sulfur? Well, what I'm going to have to do is I'm actually going to have to share one of the pairs from one of my oxygens. So I'm going to take my 2 electrons off of one of my oxygens. It does not matter which oxygen I choose. Take 2 away, and I'm going to share those with my sulfur. Okay, sharing is caring, right? So now let's take a look at our molecule here. So oxygen has 2 here, 2 there, 2 there, and 2 there. So there's a total of 8 attached to that oxygen, so it's good. This other oxygen has 2 here, 2 here, 2 here, and 2 here. So it also has 8. All right, now let's check our sulfur. Sulfur has 2 here, 2 there, 2 there, and 2 there. So it has 8. Now everything has 8, so one final check. Let's make sure we've got the right amount of electrons. I'm just going to put dots for these. So I've got 2 here, 4, 6, 8, 10, 12, 14, 16, and 18 valence electrons. All right, so that is my Lewis structure. All right, and I know that y'all have already got this down, so we'll keep on moving through our Lewis structures in the future. But there are 18 valence electrons, so that is the correct number of valence electrons. Now, how does this actually look? All right, so looking at this, right here between my oxygen and the sulfur, I've got some repulsion there. I've got what's called a lone pair on top of that sulfur. Now, a lone pair is extremely repulsive. It's very, very, very repulsive. And so what it's going to end up doing is it's going to actually push away the other two domains of electrons. So I would end up with, okay, so I'm going to take this and I'm going to actually move this other one out of the way. And let's actually redraw this shape showing that repulsion. Okay, so again, I've got my oxygen, and it's got a double bond with the sulfur, and there's my lone pair, and then that's got a bond with my oxygen. Okay, so do we see what happened there? This lone pair that is up here at the top was very repulsive, so it pushed everything else down and away. All right, and so that changed our shape, right? It originally looked like it was going to be linear, but now it's no longer linear, right? Now, instead of being linear, it's actually kind of got a bent shape, right? It took those 2 oxygens and it bent them away from that lone pair, okay? And so our molecular geometry for this would actually be bent. All right. Now, what would our electron domain geometry be? Okay, so thinking about this, remember electron domain geometry is talking about how many things are attached to my central atom. So I have 1, 2, because I've got a lone pair there, and then I do have a double bond. Now remember, it is a double bond, so there's only one bond that's actually there. Okay, so I have 3 things attached to this. Now, since it's got 3 things attached, this would be called trigonal planar. So there are 3 things attached, but again, even though I bent it, it's still going to be on that single plane, right? It's not actually going to be taking a 3D geometric shape. And so because of that, we say it's on a plane. So it's trigonal planar, okay? All right. Now, I'm going to move a little faster through this next one. I'm actually just going to go ahead and draw our Lewis structure, okay? So I have carbon, then I've got my chlorines attached to that. And then I fill my outer octets. Okay, so there is my Lewis structure right there. Okay, now let's take a look at this. So looking at this, first off, is there any lone pairs there to actually change what my shape looks like? No, there's not, right? So the shape is in general going to look like this. Now, one thing to keep in mind, though, is that this is actually a 3D shape. There is enough repulsion that can occur here that these legs can actually be pushed down and away. And so instead of being like what we see right here, where it would look like, okay, well, the angle between my chlorines here is going to be a 90-degree angle, but it's actually not, because there is enough room now, since we're thinking, again, in 3D, we can still take our chlorine that's up top here. It's bonded with that carbon, but now we're actually thinking 3D, so we've got one coming forward, we've got one going backwards, and then we've got another coming forwards. So we kind of get this 3D prong at the back, okay? Think kind of like a pyramid, but now we've also got a top to it. Okay, so I've got this kind of like that. Okay, now what we would call this shape is actually tetrahedral. Why do I say tetrahedral? Because there are 4 things attached to my central atom. Well, 4 things attached to the central atom, 4, remembering chemistry, is tetra. So this shape is tetrahedral. All right. Now, looking back at our electron domain geometry, how many things were attached to my central atom? Well, there were 4. So again, my electron domain geometry would be tetrahedral. Okay, one more, and then we will be done with this quick set of notes here. So the next one I have is ammonia. Now, ammonia is actually NH3. Okay, so I have NH3. I've got my nitrogen attached to 3 different hydrogens, and I like to go ahead and spread them all out if I can. And then I do need to add a lone pair because I need 8 valence electrons attached to my central atom. Okay, again, what does our lone pair do? Well, lone pairs push everything else away. So I have my lone pair attached to my nitrogen, and then it's going to have our 3 hydrogens bonded here. Okay, this hydrogen would be in the back. This one here would be in the front left. This one here would be on the front right. So we actually see that 3D shape again, kind of that prong like this. Now, this is just a regular prong, right? So we actually have this 3D pyramid that we have, right? The difference between it and the tetrahedral is on top of the pyramid, we also had another prong, right? So that was kind of a big difference between there and this one right here, this this NH3, this ammonia. Okay, so again, we talked about how this kind of looks like a pyramid. Well, how many sides on this pyramid? Well, there's 1, 2, 3 things attached to this. So this is trigonal, and it's actually a pyramid shape, so it's 3D, so it's trigonal pyramidal. Sometimes it's called pyramidal. So this is trigonal pyramidal. Now, again, our shape, we get this 3D shape, so a 3D pyramid. Thinking about our electron domain geometry, though, again, we're thinking about how many things are attached to my central atom. So I have 1, 2, 3, 4. Well, what's our prefix for 4? Tetra. So this would be a tetrahedral electron domain geometry. Okay? Now, real quick, this is all of those geometries written out with little diagrams so you can see them, and kind of shows you a little bit more than you actually need to know currently. Okay? So, again, how many things are attached to my central atom is over here with our numbers of pairs. Electron domain geometry is basically just counting how many things are attached to that central atom. Bond angles is just kind of helping you with drawing those shapes, making sure they're kind of looking in general 3D. Shared pairs would basically just be those actual bonds attached to the central atom. Unshared pairs would be your lone pairs. And then we've got our molecular geometry, the basic sketch of it, and then hybridization, which is what the final lesson for this will actually be. Okay, so that is everything on Vespers. Please let us know if you've got any questions. Hopefully y'all have a great rest of the day. Bye, y'all.